We share our planet with billions of creatures, sometimes very different from us. But in order to move, breed, and feed, or simply to survive, each needs to perceive its environment in an efficient way. Situating oneself in space, locating prey. This is the role of what we call the senses. There are as many perceptions of the world as there are different species. And among the 5 senses that we know of, there is one that largely prevails in humans: vision. How do animals see their environment? Are we able to see the same things as them? What can we do to see the world through their eyes? How animals see has always been a mystery that has fascinated humans. We attribute them exceptional abilities, impressed with the behaviors observed in nature or close to home. Vision is the predominant sense in humans. Even if we are very attentive to sounds and sensitive to odors, our vision remains our main sense, and we are constantly solicited by the information that surrounds us. Without even being conscious of it, we can perceive light, colors, forms, textures, movement, distance, and relief. All of this information is taken in through our eyes, but there are things that our eyes cannot see, like what's happening behind our backs. The position of the eyes on the head determines the visual field of each species. Anne Cleary and Dennis Connolly are both Irish and artists living in Paris. They are inspired by animal vision to create headsets simulating different visual fields. We asked Leah, our volunteer, to test the headsets of both artists.
Wow, this is awesome. So if I lower my head, I see little animals that are tiny below me. Try to tap my hand. You see? Not easy, huh? There are several headsets that explore animal vision. And the giraffe one is really the simplest. It simply alters your perception of the scale, and you feel so much taller.
And you see with both eyes?
Yes, I can see.
You have to get used to that. Closing one eye, open the other, alternating.
The visual field is very different from one species to another. With the chameleon headset, Leah can see in front and behind at the same time.
There are other animals that can see 2 things at the same time. Others that have eyes on the side of the head, others with a significant distance between each eye, some that can see in front and behind at the same time. There are animals that have more than 2 eyes. There are many different ways of looking at the world. And that's what led us to explore what it would be like to be a human, looking at the world in these different ways.
Our eyes being situated forwards, our field of vision is narrower than that of a horse, whose eyes are positioned laterally.
Horses have eyes on both sides with a very broad vision on both sides and a blind area in front. The horse has a blind zone of about 12 degrees. And that means that when you wear the horse headset, you see really well on each side, but since the vision is deformed, we have the impression that these 2 images are in front of us. It's very confusing. I can't see my hand.
Tap my hand. And now Anne.
Oh, I understand. So that's on the right and that's on the left.
The visual field represents the portion of space seen by an eye that is motionless and looking forward. The area that we see when we fix a point is limited. Our vision is around 120 degrees. A rabbit's vision is almost 360 degrees. Like most prey, they have eyes positioned on the side of the head and are therefore able to see what's going on behind them. An advantage that allows them to escape from predators, which often have eyes positioned at the front of the head to be precise when hunting. Simon Potier is a researcher. He works on the vision of raptors, birds of prey.
A bird of prey that hunts, like the Harris or the Aguia hawks, have what is called a rigid brow, which is very important for them, as it prevents sunlight from interfering with the retina. And this is going to increase detection capabilities because they always search for prey that are beneath them, so they don't need to see upwards. Conversely, if we take a bird hunter, for example the northern goshawk, it has a wider field of vision, it has a smaller brow, and sunlight will attain the retina. But even if it thus loses in visual ability, it will still be able to follow prey detected above.
The advantage of having two eyes that cut across the same field of vision is to allow binocular vision, which enables a better analysis of the distance that separates us from, for example, an obstacle or a prey. The image received by the left eye is offset with regards to that received by the right eye. It's the brain that adjusts both images and provides this relief effect. Anne and Dennis are also interested in binocular vision. They were inspired by the hammerhead shark that has eyes that are very wide apart from each other.
It's a challenge to be able to offer a stereoscopic depth of our world with the super binocular vision like that of the hammerhead. We met problems. Humans have a brain with limited plasticity, and it refuses to understand that vision with two eyes situated apart offers depth of vision. It prefers to think that the world is small.
Every animal has a different field of vision and suitable for its needs. If our field of vision is limited to 120 degrees, this does not mean that our view is less efficient, because other factors come into play, including visual acuity. We are able to distinguish a detail of about 1 millimeter on an object located at 3 meters from us, and certain animals have a reputation for being able to do a lot better.
It's said that birds of prey have a visual acuity significantly superior to that of humans. Well, that is not true. Some will have a visual acuity superior to humans, like the tawny vulture or the wedge-tailed eagle, because they fly to very high altitudes to seek their food, so they're going to need to see far. However, the Harris hawk, or even as extreme opposite, the Chimango caracara, which is a species that feeds directly on the ground, don't need to see far, and their visual acuity will be less than a human.
To test the visual acuity of raptors, birds of prey, 2 screens are presented to each Harris hawk, a uniform grey screen and a screen with alternating bars. Then the space between the bars is gradually reduced.
If the Harris hawk or another individual moves toward the grey screen, we give it food. If it goes to the other screen, we don't give food. When this learning and conditioning phase is over, hawks will always move towards the grey screen because it results in food. Once it heads there, we reduce the bar size, so they are much finer, which allows us to see what size bar they can discern and so at what distance they can see an object of a known size.
This experiment allows us to identify the Harris hawk's visual acuity and its ability to perceive contrasts.
What one must retain is that its vision is perfect for a task known to it, meaning it is perfect for a certain type of behavior. Birds of prey have better vision for their behavior, humans have better vision for their behavior.
But is the eye of the bird of prey, raptor, different from ours? How do our eyes capture visual information? When we perceive an image, the interior of the eye focuses on it, and light rays reach the retina. The retina is the thin membrane that lines the back of the eye. This retina is made up of two types of photoreceptor cells that play a major role in vision, the rods and cones. The cones are responsible for our central vision and color vision. The rods are involved in the field of vision, the vision of movement, as well as night vision. Our eye has three cones, sensitive respectively to blue, red, and green. It is the brain that finally recombines these three receptions to recreate an image rich of 15,000 shades. Raptors, birds of prey, have the same blue, green, and red cones, but also an additional cone.
It's one specialized in the vision of violets, of shades that they can perceive but humans cannot.
It is difficult for us to imagine the combination of colors that raptors, birds of prey, can perceive with this additional photoreceptor, and they are not the only ones that see more colors than humans. Visible light that our eyes are receptive to constitutes only a minute portion of the light spectrum. Because our senses are limited, we have access to only 2.5% of the immense range of rays. The smaller wavelengths correspond to gamma rays. Then come the X-rays that we use in radiology, and then the ultraviolet rays from which we protect ourselves. The wavelengths that are beyond the visible are the infrared, that allow us to film at night, followed by microwaves, that we use to heat our food, and radio waves with which we broadcast sound. Some species are able to capture more wavelengths than humans. This should allow them to see other colors invisible to our eyes. Mathèz-Loic is a researcher at the CNRS and works on the cognition and behavior of pollinating insects. He is interested in their color vision and how they perceive the world.
I trained bumblebees to gather pollen on flowers that had no color. The bumblebee associated the reward of sugared water, so of nectar, to this transparent platform. When I had several foragers trained, I then placed several artificial flowers that had the same shape as the transparent flowers. But this time, those flowers were of different colors. I had a blue flower and a yellow flower that they can perceive, and a red flower that they perceive as black, because they do not have the visual receptors for red. But for them, these were three different colors. And we realized that the different bumblebees chose one of these flowers at random, so one of these colors at random. As there was sugared water on each of these flowers, the bumblebees associated the sweet reward to the color of the new flower. What happened next is that the same forager always went to visit flowers of the same color. This shows the specialization of bumblebees to a certain type of flower based on color, and this is called the flower constancy.
The first research aimed at demonstrating the perception of colors by bees dates back over 100 years, in the work of Carl von Frisch.
What was very interesting in his work was attempting to separate the color and the shape of a flower to determine what importance the bees gave to each.
A water droplet is deposited on all of the colors, but only one color is rewarded by sugar water.
With always the same procedure, rewarded by a color form, for example, a yellow star. He taught the bees to forage on this yellow star, got his recruits, then after about 15 minutes he changed his cards. This time around, he inverted the colors and shapes, resulting in a yellow circle and a green star, for example. What he noticed was that the bees would systematically visit the yellow circle rather than the green star, which shows that the bees give priority to colour over shape of a flower when they make a foraging choice.
If the bees prefer to rely on the colour rather than the shape of a flower, what do we know about how they interpret the image? We know but very little about the circuits in the brain that are involved in learning and visual memory.
The first step is to develop teaching protocols using stationary bees, and we've recently developed teaching in a virtual world. We have a bee that is walking on a ball, not moving around but walking in the same place, and as it walks on this ball, it moves the virtual world which is projected on the screen around it. What we achieve is a bee that associates moving towards a visual stimulus that is rewarded and avoiding a visual stimulus that is not rewarded. So conditioning and visual memory are a result. The important question today that we'd like to answer is, how do bees see the world? We have two major hypotheses. With a compound eye, 5,000 ommatidia on each side, they can potentially see the same image 10,000 times. The second assumption is that the information of these 10,000 ommatidia will recreate a single image of the environment, as is the case of humans, actually.
If it is difficult for us to know how the bee interprets the image in its entirety, but thanks to research it is possible to determine that they are sensitive to other colours than us.
We know that these ommatidia have sensory receptors and that they are sensitive to the colours green, blue and ultraviolet. So clearly what these bees perceive visually is a mixture of the colours green, blue and ultraviolet. Theirs is a different world from ours because we are not capable of perceiving ultraviolet.
Technology can open the doors to this forbidden world. To access these wavelengths that are inaccessible to us, Richard Galley has dismantled more than one camera. Cameras are built to be adapted to our vision, to our reality. For this, manufacturers use infrared and ultraviolet filters to block this type of light ray that we are incapable of seeing.
Shooting in ultraviolet is what is most difficult. You have to remove all the original filter system and replace it by a blade like I'm doing for this customer. This is split silica, the quartz is here. This is a very white glass that lets all the rays through. And once you have that, the sensor retrieves the widest spectrum possible. After that, you have to remove all the visible and the infrared because you want to keep only the ultraviolet. So with your filter that you're going to put on the lens, you'll remove the visible, the infrared, and you're going to let only the ultraviolet pass through.
By removing the filters that block infrared and ultraviolet, we can finally see the rays that are invisible to us.
Time to try.
We gave Leah one of Richard Galley's cameras that permits observation of ultraviolet rays. She's going to test it in nature to get a better idea of bee vision. Plants are dependent on insects to ensure their reproduction. By foraging one flower after another, they are going to disperse the pollen. Flowers have developed many strategies to get noticed and attract insects. The camera reveals an ultraviolet world, quite different from what we are used to seeing. Ultraviolet patterns are more often found at the flower's center where the pollen is kept. The function of UVs would therefore be to guide the insects and to facilitate the discovery of the precious nectar. In ultraviolet, it is not only the flowers that change. Our freckles appear much more marked, and sunscreen has completely changed colour. Some species are able to see elements invisible to us by using a range of the spectrum that is inaccessible to us. And it is not just in colours that we are limited. When light decreases, we are not on equal ground with certain representatives of the animal world. Even if we are mammals, with certain species close to us, the differences in night vision are considerable. Most vertebrates can see in the dark. Their eyes have a structure, the tapetum lucidum, which allows them to increase the amount of light captured by the retina. It is this structure which makes eyes shine when hit by light. But not only mammals can see at night.
To see at night, nocturnal birds of prey have three major characteristics. The first is eye size, very important to nocturnal birds of prey. So, by increasing the size of the eye, this increases the number of photons of light that will enter the eye, and so they'll perceive more light. Then there is the size of the pupil. Increased pupil size also increases the number of photons that will enter the eye and attain the retina, resulting in better vision in low light intensities. The final characteristics are the rods that allow seeing at night when there is little light intensity. And for these three reasons, nocturnal raptors can see very well at night, at least compared to diurnal raptors and humans.
In the day, guided by reference points, we are able to follow a direction without any difficulty. But at night, we have much more difficulty in finding our way. The infrared camera attached around Leia's waist reveals that her progression is considerably less assured. Our night vision is not very efficient compared to that of a cat that has a 6 to 8 times greater vision in the dark than we do. However, our night vision slightly improves when we remain in the dark, thanks to the effect of rhodopsin, a light-sensitive pigment that takes up to 45 minutes to regenerate in humans, then allowing maximum sensitivity. No eye, however sophisticated, is able to see in total darkness. All eyes in the animal world function with light, and even a cat is unable to see in complete darkness. But one nocturnal animal has sidestepped this problem, seeing with its ears. Cyril Schambachler is passionate about bats, an animal that lives at night and that we know little about.
Here we're hearing the common pipistrelle, which is hunting, because that sound is very fast. Sometimes you really hear an acceleration, and that's what we call a hunting buzz, when it's going to capture an insect. There's a second or less with no noise, then it's swallowing, and then it starts emitting again. There was a buzz.
The speed of bat movements and the absence of light makes them difficult to observe. To understand them, you need a trained and attentive ear. Cyril has, over the years, learned to see with his ears.
The detector I have allows making ultrasound audible. What is fascinating with the acoustics is that alone in the dark we see nothing, we don't see bats, we hear them. We can determine the species and what it is doing. We know if it is just transiting, if it is hunting, if it has captured something, all thanks to sound and without seeing anything.
If we can't see them well, how do they see? Are they able to use their eyes?
In fact, bats have eyes that are perfectly functional. They see perfectly. Simply, their eyes are tiny, and echolocation, not vision, is their most developed sense. There have been experiments where they were blindfolded and even their eyes removed, but they could still find their way without a problem, and that was in fact the first realization that they had another sense that we knew nothing about. They emit ultrasound, most by the mouth, some by the nose, and the ultrasound will hit an obstacle. This obstacle could be prey, could be us, could be a wall, a tree. Then the echo will be analysed by the brain, and you have to imagine that bats build an image of their environment in black and white, but in 3 dimensions. The horseshoe bat is able to detect a thread thinner than our hair. They have completely phenomenal precision in their ultrasound, and they have a 3-dimensional map of their environment. Their ultrasound goes so fast that they adapt, even when flying at enormous speed in the treetops, for example. They can go very, very fast in completely crowded environments where we wouldn't even advance a meter.
Thanks to rapid and directional sound waves that bounce off the surrounding objects and return to their ears by echoes, bats perfectly determine the space in which they evolve. Echolocation allows them to avoid fixed obstacles with ease and speed. And even when it comes to moving obstacles, like a fellow bat, they show extreme precision in avoiding each other.
All rhinolophs emit by the nose, and they have this very particular horseshoe-shaped nose sleeve that allows them to concentrate their ultrasound. And their large ears are like 2 large satellite dishes that can move separately, so they are extremely accurate. So depending on their habitat, based on their prey, they have different types of ultrasound and different emission intensities too. It has been calculated that the Leisler bat has a maximum emission strength that's almost as intense as the sound of a plane taking off. So good thing it's ultrasound, otherwise it would be painful to us. We even think that they actually use this power to audibly knock out their prey. They send out a very, very strong cry, and it knocks out the butterfly.
If all bats do not practice echolocation, those who do have turned the use of their ears into a second form of vision, acoustic vision.
It's because of their acoustics that bats have a 3-dimensional vision of their environment. So yes, we can say that this is an acoustic vision. In fact, they have an image like ours, but in black and white and with the volumes. Very accurate volumes. All of the bumps, everything, but not thanks to eyes, but to sound.
For feeding or moving in the dark, the bat isn't the only one that can see without using its eyes. Most snakes have very good vision during the day, but when it gets dark, some, including rattlesnakes, boas and pythons, have infrared vision. Organs between the eye and the nostril, called pit organs, take over. By capturing infrared radiation, they allow these snakes to perceive the heat present in their immediate environment. These organs are essentially sensitive to wavelengths of 5 to 30 micrometers. Humans give off heat in the form of infrared radiation at around 10 micrometers. These snakes can easily detect us at night. This thermal vision is not perceived by the eye, but nevertheless forms a picture in their visual cortex. pit organs have two functions. They allow these reptiles to identify places where they can warm themselves, and they allow hunting warm-blooded animals. At night, when the thermal differences between prey and surrounding temperatures increase, the hunt is easier. A rattlesnake can sense a mouse 40 centimeters away. When we gave Leia a thermal camera, she can perfectly distinguish the sources of heat in her environment. The hottest areas range from yellow to white, and the colder from blue to black. Our daily lives in infrared vision would thus be very different. Colors, light, visual field, heat. Technology allows us to understand what animals perceive. And there is one thing the cameras have allowed us to do for some time now: the ability to speed up or slow down time. Like many insects, dragonflies are able to perceive movement in a much more precise manner than we are capable of. If a dragonfly had to watch a movie at the same time as us, it would only see a sequence of still images, and they would be jumpy and in slow motion. Is their perception of time and events different from ours? The human eye perceives fluid movement as of 25 images per second. The dragonfly distinguishes 175 images per second, so is able to see its surroundings by better breaking down each movement. Its brain is capable of processing many images very quickly. Extremely slowed images bring us closer to their vision. Hardly observable to the naked eye, the movement of the dragonfly in flight becomes perceptible. This vision gives them a significant advantage. They can spot prey and predators just in time. What would happen if we were equipped with the same faculties? Lorenz Potast asked himself this question. Interdisciplinary engineer, his work is often related to an artistic approach. He has created a headset allowing to see the world in slow motion.
So it works in that way that there's a little camera in the front that sends the video signal to a computer in the inside, and from the computer it is processed and it can be slowed down with this remote control and is then displayed on some video glasses right before the user's eyes and simultaneously on this display on the outside. Now I'm going to slow you down to, let's say, 70%. Okay. You see from this point on, whoa. Yeah, that's your weird. Knowledge about what your body is doing and what you're perceiving from it visually is differentiating. Now I can even slow you down more to, let's say, 30%. And now if I do some interesting slow motion stuff, like some jumping, you're gonna see it very slow. After everything has been slowed down now, it's captured. I can also fast forward you again. So, hello again.
Hello.
Our volunteer undergoes several experiments with the Lorenz's headset. With slowed vision, can she fill a glass of soda without spilling any and without relying on gravity? Catch a ball in flight, or even light a candle? Seen from the outside, time seems long between the moment that Lorenz blows bubbles towards Leia and when she sees them and tries to grab them. When she perceives that the glass is just starting to fill up, it's actually almost already full. Her perception of movement is clearly altered. We are therefore very far from the dragonfly's faculties of anticipation. How is it that Leia fails to anticipate her movements while experiencing slowed vision?
Yeah, when you're wearing the helmet, it mostly feels disturbing, to be honest. So it is not what you might expect, especially relaxing or slowing down experience. It is very confusing because the first thing that happens is that if you have something slowed down, let's say 50%, then of course it takes double the time to play back, to relive it. And thereby very fast you got a delay as well. So you lag behind of what's happening in the real world. And thereby you somehow, you still receive the input from your other senses, but your visual sense and your other senses are not synchronized anymore. Are you okay?
Yeah, I'm fine.
Okay. I thought about the different perception of time for humans or animals quite a lot during this project. And the funny thing is, and I know that there's some scientific research about some animals that can perceive faster, but I think for them it feels normal. So and this is somehow what this project shows, the limits of what you can perceive.
Our brain is not accustomed to receiving this kind of information and does not know how to treat it in order to coordinate an appropriate response. Color processing, detection of movement, assessment of shape and form, the role of the brain seems to be predominant in vision. Is it not ultimately more important than even our eyes? Yves Rossetti is Professor of Physiology and a researcher in neuroscience at the CNRS. Leia and he will test the involvement of the brain in the visual process.
So, let's start by checking that your motor skills are well in line with your vision by throwing these little brains into a basketball net.
All right.
Very good. Perfect.
Great, got it.
That's it. One more. Perfect. Now let's try these glasses. What I'm going to ask you to do now is to aim for the blue basket.
Okay, can I open my eyes?
Yes, open your eyes and aim for the blue basket.
Okay, there it went completely left, didn't it?
It seems so, yes, the blue one.
Yes, but I aimed to the right, but it didn't work at all. It's really strange.
You're aiming more to the right than the blue, right?
Yes.
Fitted with glasses that deviate her vision to the left, spontaneously, Leia would tend to aim for the orange basket, so she has to train to aim for the blue basket.
Is it becoming natural?
Yes.
Then let's remove the glasses
Okay.
and we'll continue the experiment. So this time, aim for the other basket, the orange one.
Oh my, okay.
In the beginning with the glasses, we asked you to target the blue and the glasses shifted your vision of the blue, so it was here, so you attained the orange.
Yes.
And if you were perfectly adapted to the glasses, if you had kept them on long enough, when you had removed them, we'd ask you to aim at the orange and there you'd hit the blue. When the volunteer puts on the glasses, the perception of the surrounding world remains pretty much unchanged, except that it is shifted in space, so vision does not give any information about the errors produced by the glasses. On the other hand, when moving in space occurs, at that moment action will be directed towards the shifted vision. That is to say, that to reach a point that is here, you have to aim for another point, for what is called the virtual image of the object in terms of optics. And so the action is like the vision's reality test.
This experiment illustrates very well the role of the eye as an intermediary in vision and its codependency on the brain in our perception of the world.
Thank you.
So if the brain and eyes work together, what happens when they don't agree?
I'm getting there now.
Now let's visit the tilted house.
Okay.
So look this way. It's a house in which everything was scrupulously glued vertically, and then,
Okay.
once construction was finished, we lifted it to tilt it 15 degrees. The best way to know what the true vertical is to use a builder's plumb line. So I propose adjusting this so that it complies with your perception of the vertical. The tilted house experiment will demonstrate different things. Firstly, it shows the importance of vision in encoding information on gravity. It's rather curious, since vision is not specialized in the analysis of gravity. We have our inner ear for that, the vestibule, which is specialized in encoding gravity and terrestrial attraction. Despite the presence of this organ specific for that, despite the presence of receptors under the soles of our feet that indicate the differences in pressure, of muscle receptors that tell us our posture, we realize when Leia opens her eyes that she is drawn to the right, to align with the visual information that she unquestionably knows to be false. She knows that the house is tilted and cannot prevent her brain from using this information to keep herself standing so-called straight, and so she's not standing straight. So that's the first thing. It shows the extraordinary force of visual information. And that comes from the fact that vision is the most important sense in humans for encoding space. Vision is the sense that occupies the greatest surface of our cortex, and given the habitual reliability of visual information, the brain attributes great trust to visual information. And when disturbed in the tilted house, even if the other information remains reliable, the brain continues to trust the visual information. After the vertical, where is the horizontal? I've positioned this bar and ask you, which way does it lean?
It's higher on the right, isn't it? I'll bet it's horizontal, isn't it?
Why would you imagine horizontal?
Well, because everything is off, so I must compensate, but I still find it very high on the right.
Then, if I take a ball, I throw it up, then it comes down.
Wow, amazing. So it means it's lower on this side.
That's it.
Okay.
In optical illusions, we're in a different circumstance because, in general, there are no conflicts between vision and other sensory modalities. In this case, it leads to conflicts between what are called qualities of the visual modality, so shadows, movements, shapes, depth and color, for example. We are used to using contextual information because they allow us to better understand the stimulus we are trying to analyze. And this importance of context is found in many optical illusions, like color illusions, where one can vary the perceived color of an object based on the color surrounding this object. One can vary the perception of the size of an object by the size of the objects that are located around the object. So context is something absolutely fundamental that we often use without knowing, and which gives place to a number of optical illusions.
So what is interpreted in definitive is largely dependent on context. Here, two circles are flashing at the same time. When the color of the background changes, the brain interprets this as asynchronous flashing. Perspective can also play tricks. In this optical illusion, the circle on top looks bigger than the one on the bottom, but they are actually the same size. Here, if we stare at the cross, a green circle appears after a few moments. And this is a fiction created by our brain. If we shift our eyes from the cross, pink circles appear instantly. The brain is not interested in constant information and prefers change. It naturally replaces the missing pink circle by a green circle and thus creates movement. Light and shadow play also affect our interpretation of an image, so dip or bump. And what do you see in this image? A rock between two bricks, perhaps? Once the illusion is revealed, the image will never be seen and interpreted in the same way. At the center of this image hides an object. The object in the wall is in fact but the ash of a cigar. The brain chooses the more realistic interpretation.
The primary job of the brain with vision is to extract information. The information that attains the retina is extremely degraded because the light has to go through all the retinal tissue and all of its cells and vessels that are interspersed between the arrival of the light and the receptors. And the cones and rods are at the back of the retina. The brain has to do a lot of analysis, and the retina starts this analysis to extract from a very noisy, degraded signal. Signals that allow us to really distinguish shapes and colors in our visual information. And from there, the brain is able to interpret the signals it has received. It can choose to add or remove certain things depending on the circumstances. For example, removing the nose that is useless to see since it is constantly between both eyes and adding relevant information that is missing.
Our vision is the result of what our eye perceives and what our brain interprets. Animals, based on their needs, can have abilities that seem inaccessible to us. But with the progress of science and the miniaturization of technology, we can imagine the conception of lenses that bring us closer to these superpowers. Seeing ultraviolet and differences in heat, zooming in on a detail. In reality, we are still very far from such achievements, even if in the field of health, applications are beginning to emerge. Professor Thomas Wolfensberger is an eye surgeon specializing in the retina and receives numerous patients.
There are two parts of the system that are indispensable to vision, so the retina and the optic nerve must be in good condition.
He is one of the few surgeons to have performed a retinal implant for patients suffering from retinitis pigmentosa. Retinitis pigmentosa is a genetic, degenerative eye disease characterized by progressive and gradual vision loss leading to blindness. It occurs most often between the ages of 40 and 50. The bionic eye consists of an implant placed within the retina.
What we do with the implant is bypass the problem of light. The retina is no longer stimulated by light because the cells that react to light are no longer there. So we directly stimulate a higher level with electricity because, since the rest of the retina is an electrical network, it reacts to electricity. And that's the principle of this prosthesis.
In order to capture images, the patient wears a pair of glasses with, at the center, a camera connected to a handheld computer. This computer decreases the image to 60 pixels in different degrees of gray. It then transmits the information to the implant.
It's an implant that is surgically positioned around the eye with what we call a scleral buckle. It is something that is very standard, used all the time in ophthalmology. The only thing that is particular is that we fix a radio receiver to this buckle, which will receive information from the system carried on the outside by the patient, which are retransmitted by impulses that activate the surface of the retina like a pacemaker activates the heart.
These electrical impulses then use the normal visual channels to send information to the visual cortex and generate an image. But it is unclear how the image is interpreted at the level of the brain. It is impossible for us to represent what patients who wear the implant see compared to a vision considered normal. We are very far from imagining that inside Charlotte's eye hides advanced technology.
A month after surgery, several months of therapy began. Learning to analyze the environment. If you detect something on the wall, you have to determine a form to better deduce whether it's a table, a mirror, or a poster. Something that I really enjoy when I pick up the kids from school in the evening is seeing all those silhouettes of people and guessing. She's wearing a light-colored top. She's wearing dark pants. That kind of thing. You end up getting used to not seeing. You have to relearn to see.
People who are blind are generally well adapted to blindness, so there are many things that they can do on their own. However, this adds security, added independence. It allows one to do things, perhaps with a little less help from someone else.
After getting the implants, I continue to do everything, but with perceptions. When I speak of this new vision or perception, I notice people think I'm talking about seeing again like them, but it's not like that. I always prefer to clarify that it's a form of vision, or that it's a new kind of vision. When you spend 10 years without any visual information, and all of a sudden You're able to orient yourself in your environment by detecting things like a door, a tree, things like that. Well, it changes everything.
The implant is currently connected to a standard camera, but couldn't we conceive using other types of technologies to which our eyes have not access, and thus provide patients with a totally different vision?
We can imagine giving patients ultraviolet, X-ray, infrared, and thermal information.
Even though technological advances are useful and permit better living conditions in certain cases, our biological performances are scarcely reproducible artificially. Our vision, a very perfected function, and we are still nowhere near equaling the millions of years of evolution that forged this incredible tool that is our eye. Animals have multiple ways of seeing the world and will continue to intrigue us. There will always be a mystery when an animal looks us in the eyes. But thanks to advances in technology and science that reveal an inaccessible universe, will it be possible to get closer to the animal world?